Hi, thank you for coming to the poster presentation. Um, this project is to estimate the calorie from 2D photo. There are many apps that doing that, and still the challenge is in the inaccurate estimations of calorie. I specifically focus on the volume estimation, in particular the depth map. So basically, when um, the distance from camera to the lens to the food, that is depth map, and that estimation is where I'm focusing on. So um, when the food shape is irregular, then that depth map estimation become a little more noisy. So I try to address it by improving the algorithm by adding constraint into the loss term. To give you the overall idea, this diagram explain the how the model structure. To start from the data RGB image, that's a 5,000 um, pictures, the sample pictures, um, publicly available and released by Google. Um, and that picture took in the more of environment kind of lab. And using that, I set up the encoder by using ResNet 50 convolution neural network. And here I have a two head. Head one is a depth estimation. And the second head is the identifier, so that this is where food classified, and it has a lookup into the corresponding density. So multiply that together, basically give you the calorie. This project is focusing on these head one depth estimation. Um, and here the loss function in depth one, the depth estimation. These are the mean square error, the loss function, and I added the physical constraint where it penalized the surface curvature to enforce the smooth, more sensible geometric surface, and so um, that as a result, here is comparing the error. So base case is the first one. It compares the MAPE, the percentage error, between train and test set. So 5.36% and 5.77% is the baseline case. And then once I add the loss term for the physical and retrain, then error came down significantly to 0.71%, and test set shows uh 0.89%. So the overall improvement in train and test is about 7.5 multiple the x and 6.5 um x. I think the as a result, like you see that physically informed constraint really improve the estimation, and I use overfitting techniques by adding um, the randomly select sample for photometric augmentation for lighting, plus minus 20%. And so that makes sure the model learn from geometry, not from lighting. And also I apply the dropout 50%. As a result, the gap, the difference between test errors and train errors are within 0.18% percent point. Also, I did the stress testing by adding um, the um, the lighting and the same technique that I did for uh, the overfitting in photometric augmentation. But this time the range is a bit larger, so that zero point 0.4 is applied to darken the pictures, and 1.6 is to brighten. And these are the pictures. And the first one is original, next one is a dark one, and the third one is in a bright color. Made vary from 0.42% from the original to 0.76% to bright one. And so the variance is less than 0.5%. I can see that that also support the robustness of the algorithm. The end-to-end calorie was calculated, and it was benchmarked to the reference here in state of art. Its benchmark is about 14% in calorie estimation. However, I wasn't able to beat it, and primarily the segmentation head is not added into this the model structure yet. In particular, math to former semantic segmentation will be very helpful to isolate the food from the background plate, first of all, and then when there are multiple food and then also isolate and add segmentation each other, so that will improve, and that's a future work. I also did I tested for the scale and creatively using the 3D meta food data and using distance from 3.3 meter to 2 meters. And in this simulation, the error was reduced quite a bit from 83% to 1%. However, still, this has to be tested with a more of the realistic setup with the phone. And the future work remaining is about the more of a realistic food picture in actual cafeteria setup instead of, the sample that was taken in more of the control environment. So that's the overall work. Thank you for the listening to this poster presentation. Thank you so much. Bye.